Let us discuss about another application of Gauss's theorem, that is electric field due to an infinitely long line of charge. This is that line of charge xy. It's an infinite long line of charge charged positively with a charge density lambda. Charge density lambda or linear charge density can be defined as a charge given per unit length. So that means it can be defined as lambda is equal to capital Q divided by capital L, where capital Q is the total charge given and capital L is the entire length of the conductor. It is also true for a small amount of charge given on a small length of the conductor. Let small q be a small amount of charge given on a given length of the conductor L, then lambda can also be defined as Q by L. So this is that conductor of uniform charge density lambda. My aim is to find electric field at this point P at a distance r from the conductor. So in order to find electric field using Gauss's theorem, I need to construct a Gaussian surface. In this case, it is a case of linear symmetry, line symmetry. So I have to construct a Gaussian cylinder of base radius r and height L. So this is that Gaussian cylinder of base radius r and height L. Then question arises, how much charge is enclosed within this Gaussian cylinder? In order to find out charge enclosed within this Gaussian cylinder, I have to multiply charge density lambda with the given length of the conductor. So given length of the conductor means length of the conductor which is enclosed within the Gaussian cylinder, that will be the height of the cylinder itself. So the charge enclosed within the Gaussian cylinder will be Q is equal to lambda into L. Put as equation number 1. Now I am going to take three elemental areas. The Gaussian cylinder has three different surfaces, two end surfaces and one curved surface. Once again, two end surfaces and one curved surface. I have to take equal elemental area on two end surfaces and a curved surface. One first end surface is denoted by letter A, the second end surface is denoted by letter B, and a curved surface is denoted by letter C. So I am taking equal elemental areas on A, B and C. You already studied that area vector is perpendicular to the area. So area vector will be like this here, area vector will be like this here, and area vector will be like this here. Since it is positive charges, electric field will be like this, radially outwards. Now, the flux contribution, according to Gauss's theorem, the total flux phi is equal to charge enclosed within the Gaussian surface divided by epsilon 0, but the total flux contribution is due to three surfaces. Integral of surface A E dot ds plus integral of surface B E dot ds plus integral of surface C E dot ds. So the total flux through the entire Gaussian surface can be subdivided into three: surface A, surface B, surface C. Now look at surface A and surface B. E and ds are perpendicular to each other. When E and ds are perpendicular to each other, the flux phi will be integral E ds cos of 90, that will be 0. So that means there is no flux contribution due to end surfaces A and B. Only flux contribution is there due to curved surface C. In the curved surface you can see E and ds are parallel to each other, therefore theta is equal to 0. Therefore, since there is no flux contribution due to end surfaces A and B, only this contribution remains, and that will be integral C E ds cos of 0 is equal to Q by epsilon 0. Why cos of 0? There is no angle between electric field and area vector here. Since cos of 0 is equal to 1, I can write integral E ds is equal to Q by epsilon 0. Now, everywhere on the surface of the cylinder, everywhere on the curved surface of the cylinder, electric field must have the same value due to symmetry. Since electric field is having same value, I can take it out. E into integral ds is equal to Q by epsilon 0. Put as equation number 2. Now the next question arises, what is integral ds? Integral ds is nothing but the total surface area of the curved surface, because that only provide flux contribution. So I have to find out total surface area of the curved surface. Two end surfaces will not contribute to the flux. The total surface area of the curved surface is 2 pi r into L, where r is the base radius and L is the length of the cylinder. Put as equation number 3. Now I have to substitute equation number 1 and equation number 3 in equation number 2. When I substitute equation number 1 and 3 into, I will be getting E into 2 pi RL is equal to lambda L by epsilon 0, because instead of Q I want to substitute Q is equal to lambda L. So L and L cancels. What remains? E is equal to 1 by 2 pi epsilon 0 lambda by R. So I can multiply and divide by a 2, then this quantity become 1 by 4 pi epsilon 0, and when I multiply by 2 here, this become 2 lambda. So the result will be E is equal to 1 by 4 pi epsilon 0, 2 lambda by R in the unit vector R, because electric field is a vector quantity. Another application of Gauss's theorem is electric field due to an infinite plane sheet of charge. Electric field due to an infinite plane sheet of charge. So this is that infinite plane sheet of charge. It is of definite magnitude only. That only we can draw, because an infinite plane we cannot draw in a paper. So this is that sheet of charge. Let A is the area of the sheet and sigma is the charge density. It may be either positively charged or negatively charged. Let us take positively charged sheet of charge, and sigma is the charge density. So our aim is to find electric field due to this sheet of charge at any distance. Let the distance be x. At that distance, I have to find out electric field due to this sheet of charge. So in order to find out electric field, I have to construct a Gaussian cylinder. But this Gaussian cylinder is placed like this horizontally, bisecting the sheet of charge, extending either side equal distance, and this type of arrangement is called a pillbox. So the Gaussian pillbox is constructed. Now how many surfaces are there? The Gaussian pillbox is constructed with a base area ds. Base area ds means end surfaces of the Gaussian pillbox is having an area ds, and I'm taking an elemental area on the curved surface of the Gaussian pillbox also. The curved surface is denoted by C. Now you can see the area vector is like this. At the end surface A, end surface B, area vector is like this, and on the curved surface, area vector is like this. Since it is a positively charged plate, you can see the electric field is radially outwards. Since the electric field is radially outwards on either side, you can see on the curved, on the end surfaces A and B, electric field and area vector are parallel to each other. But on the curved surface C, electric field and area vector are perpendicular. So here electric field and area vector are perpendicular. Whenever electric field and area vector are perpendicular, that particular surface will not contribute to the flux, because flux E is equal to E into ds cos of 90, that becomes 0. So again I am going to apply Gauss's theorem. When I apply Gauss's theorem, total flux passes through the Gaussian pillbox is equal to flux due to end surface A plus flux due to end surface B plus flux due to end surface C is equal to Q by epsilon 0. So as I explained, end surface C will not create any flux while electric field and area vector are perpendicular to each other. Therefore, it will not create any flux. Electric field and area vector are perpendicular to each other. So let us avoid this flux due to end curved surface C. Then what remains? Phi is equal to phi A plus phi B. That is equal to Q by epsilon 0, where Q is the charge enclosed within the surface. Now what is phi A? E ds cos of 0, that means, or E dot ds. Here this flux is also E dot ds. That must be equal to Q by epsilon 0. So that means 2 times E dot ds is equal to Q by epsilon 0. Now what is angle theta? Angle theta is equal to 0. Electric field and area vector are parallel to each other in both surfaces. Therefore, 2 times E ds cos of 0 is equal to Q by epsilon 0. Since cos of 0 is equal to 1, therefore 2 times E ds is equal to Q by epsilon 0. Put as equation number 1. Now what is this Q? This Q is the charge enclosed within the Gaussian surface. This is the entire charge, and the charge density remains same for the entire section of the sheet. Now I have to find out the charge enclosed within the Gaussian surface. This is the charge enclosed within the Gaussian surface. The charge density helped me to find out charge enclosed within the Gaussian surface of area ds. So you know sigma is equal to total charge divided by total area, as well as sigma can be written as charge given on a small area divided by the magnitude of that area. Q is the charge given on a small area ds. Therefore, sigma can be written as Q by ds. From this equation, the charge given in that area ds, or charge enclosed within the Gaussian surface, Q is equal to sigma into ds. Put as equation number 2. Now I have to substitute 2 in 1. When I substitute 2 in 1, I can see 2 into E ds is equal to, instead of Q, I want to substitute sigma ds divided by epsilon 0. So that means ds cancels. What remains? E is equal to sigma by 2 epsilon 0 and a unit vector x, because electric field due to any charge distribution is a vector quantity. Now look at this particular equation. One thing is very clear, because the electric field due to an infinite sheet of charge is independent of distance. So irrespective of the distance, and everywhere on the right hand side as well as on the left hand side of this particular infinite sheet, electric field remains same. That's a uniform electric field, and its magnitude is sigma by 2 epsilon 0. But it is very difficult to realize practically, because an infinite sheet of charge is very difficult to realize practically.